explain the behavior and the characteristics of acids and bases. All right, so the first thing that we're going to talk about is what are acids and what are bases. And we'll take a look at some differences between them. So, acids generally, we can recognize them because they contain hydrogen in their formulas. Right, that's a quick way to identify an acid, and that H is usually written first in the chemical formula for an acid. Acids are things, when you add them to water, when you dissolve them in water, they actually dissolve by breaking apart into ions. And specifically, the ion that makes an acid is this one, that H+. We're going to see this throughout the entire chapter. Acids are things that are going to give or produce those H+ in water because ions are produced. All right, just like when we saw our solutions earlier in the solutions chapter, when ions are produced, that makes those things electrolytes, right? Charged species allow the conduction of an electric current. So acids generally contain hydrogen. They break apart to give you ions, specifically the H+, the hydrogen ion, which means that they're going to be electrolytes. Taste of acids. Now, we don't have you taste acids in the lab for obvious reasons, but you probably already know what acids taste like because lots of foods actually contain acids in them. Can you think of a couple places where the food is acidic? Or a couple types of food, I'm sorry, that are acidic? Vinaigrette. Okay, contains vinegar in it, is that right? Okay, so vinegar is an acid, by the way. You ever, taken a shot of vinegar, if you're into that thing, has a specific taste. Any other types of acids? Fruit? Citric acid that you find in citrus fruits, right? That's an acid. So if you ever bit into a grapefruit, right, you can kind of think of, and maybe your face is making the face that you would make when you bite into a grapefruit. It's, how does it taste, grapefruit? Besides delicious and pretty good, describe it better than that. It tastes sour, right? So that's the typical taste for acids. They taste sour. Probably the most common test for acids is how they interact with something called litmus. And litmus is an example of what's known as an indicator that changes color, dependent upon whether it's exposed to an acid or a base. And acids turn litmus red. So if you have a piece of litmus paper and you stick it in an acid and it turns red, right away you know that you have an acid. There are many types of acids out there. Some are more common than others. So let's take a look at some of the more common acids. I'm going to highlight some of these, which means that you need to know them. Names and formulas. The very first one, HCl, which is hydrochloric acid. Very common acid. We use it in the lab. You've actually used HCl in the lab already a couple times. When you use it, I told you to be careful with it because it's a strong acid. But you also find HCl not just in the lab. You actually don't have to go too far to find hydrochloric acid. It's in your stomach. Right? Stomach acid is HCl, it's hydrochloric acid, and it's a very strong acid. And it needs to be to break down all the the stuff that you eat and drink. A second very common one is nitric acid, HNO3. Extremely strong. The third strong one, and we'll talk about strong versus weak down the road, is sulfuric acid, H2SO4. And that's what you find in your car batteries, right? That's battery acid, sulfuric acid. There are a couple of weak ones that we're going to encounter as well. So there's carbonic acid, H2CO3. Okay, and that's what happens whenever you have carbon dioxide dissolved in water. So for example, all of your carbonated beverages, right, what makes them carbonated is the fact that you have carbon dioxide, right, a gas dissolved in it. And that gives them a little bit of acidic taste. The one right under it, acetic acid, HC2H3O2, is what vinegar is, right? Vinegar is just a dilute solution of acetic acid. And then the last one is the one right under that, which is phosphoric acid, H3PO4. And that is also very commonly found in different types of drinks, right? So whether it is a soda that you're drinking, whether it's a root beer or a Diet Pepsi or a Coca-Cola or a Dr. Pepper, right? A lot of times they're going to contain phosphoric acid in there, not just to, make your teeth decay, because that's what they do. They break down your teeth, but to help enhance the shelf life of some of those things.
What did you say we found nitric acid in?
Nitric acid is just a very, very strong acid, right? You're not really going to find that in most common everyday things. It's a little too strong for normal everyday applications. All right, so those are some characteristics of our acids and some common acids that we're going to encounter. So bases, on the other hand, in contrast to our acids, bases are things, typically when they dissolve in water, they're going to make or they're going to produce the hydroxide ion, OH-, which means they will contain hydroxide in their formulas. So for example, sodium hydroxide has NaOH in it. When we dissolve sodium hydroxide in water, it is also going to break apart into ions. And what makes it a base is the fact that it produces the hydroxide ion in solution. Right? And we can tell really quickly that something is a base, not always, but most of the time, because it has that hydroxide, that OH, in its chemical formula. Right? So the OH come together. That's a polyatomic ion that you see. Bases have tastes that are different than acids. So bases, in contrast to acids, acids we said taste sour, bases actually taste bitter. So B for base, B for bitter. And sometimes, depending on the type of base, sometimes they taste a little chalky. So if if growing up, if you were one of those kids that had a potty mouth, what did your parents do to you? They put soap in your mouth. Does anybody remember that happening to them? Maybe you were all, angels, but I have a feeling not. How did it taste, if you can remember? When you tasted soap, either on purpose or by accident, whatever. It burned a little, right? So, you can do this at home if you want to, stick a bar of soap in your mouth and see what it tastes. But I'm going to tell you, it tastes bitter. It happened to me a lot when I was growing up. So a bitter taste associated with a base, and other types of bases also taste chalky. right? So if you think of the last time you had to take some sort of an antacid for something, right? A lot of times they, whether it's Tums or something else, they taste like chalk, right? It's really bad taste. It's actually chalk that you're eating. It's chalk, like the stuff you write on the board with. That's the active ingredient in your antacid. They just add some flavoring to it, right? So it doesn't taste as terrible. But that's what it is. So very different than the taste of acids. So because they give you ions, these are also going to act as electrolytes. Bases have a feel associated with them, right? So they actually feel slippery to the touch. Right? Again, if you think about soap, right, being a base, and obviously soap is slippery because it actually is a base. It's made from bases. I'm not going to tell you what they're actually made from because that might gross you out, but a lot of your soaps are actually made from bases. And then in terms of litmus paper, very different also than acids, right? Bases turn litmus. So we said B for base, B for bitter, B for blue, right? So litmus, bases turn litmus blue. In terms of what we're going to look for in a base, I mentioned that typically you're going to find the hydroxide ion and the OH as part of their chemical formula, right? And that's what you're going to see in most cases where bases contain that hydroxide. So sodium hydroxide, for instance, would be an example of a base. The one at the bottom, aluminum hydroxide, that's often found in a lot of your antacid type drugs. Sodium hydroxide, very, very common base. It's actually found in stuff like Drano. And there it's also called lye, L-Y-E. All right, so lye is just a regular name for sodium hydroxide. If you go take a look on your Drano bottle at home, turn it around, look on the ingredient label, the first thing they list on there is sodium hydroxide. Right, it's a very strong, it's a very concentrated NaOH that does what it's supposed to, which is to unclog drains and whatnot. All right, so just a quick summary here. This is a really good summary actually in terms of some of the properties, the characteristics of acids and bases in terms of things that we won't have you do in the lab, like how they feel and how they taste, but then also some other chemical reactions in terms of what they do to each other, and then their ability to act as electrolytes or non-electrolytes. Okay, questions so far on acids and bases? That's a quick intro to it, just in terms of some of their properties. We're going to dive a little bit deeper now into how we define our acids and bases. And there are several theories that we can use to describe and explain the behavior of acids and bases. If for whatever reason you decide to go further into chemistry, which I know a lot of you are not planning on doing that, but if you decide to take other higher levels of chemistry, you will look at other theories that describe acids and bases. But for our class, we're going to focus on one that is, it's a simple theory, or not simple, it is it's a short theory, but it actually encompasses lots of different acids and bases. And this is called the Bronsted Lowry theory of acids and bases. So Bronsted Lowry, often abbreviated as BL, for Bronsted Lowry. And this treats acids and bases according to their ability to lose or gain one thing. And that thing is called a proton. So, according to the Bronsted Lowry theory, an acid is a proton donor. In other words, it gives up or loses protons. Well, what's a proton? A proton is the same as an H+ ion. Hydrogen ion, proton, same thing. So the ability of something to lose or give up a proton is an indication of its acidic nature. All right, so let's take a look at how this can happen with a simple example of HCl in water. I'm going to redraw these Lewis structures here on the right side. So HCl looks like this. And water looks like that. So in this, all I've done there is just drawn Lewis structures for those things, right? They should look familiar to you. Water, you've done that several times already. And then HCl is just the H connected to the Cl. So HCl, we just said, was one of the many acids. So we would predict that HCl is going to act like an acid. So according to the Bronsted Lowry definition, HCl here is going to act as an acid. It is going to donate or lose that H. Where is that H? Not just an H, the H plus. Where is that going to go, do you think? Where's the only place that it can go? The only place that it can go would be to the other thing in the reaction, which is the water. So if I take away an H plus from this, what do I end up with? What does this become when I remove an H plus? I end up with Cl, which is now going to have a negative charge, right? So we end up with Cl minus. And then what would form if I stuck an H plus onto that thing? I'm just sticking an H plus onto it. So let's draw what we already have. And then I'm going to add an H plus onto it. It looks a little unusual, yes, but that's what happens. So we end up with this thing here called H3O plus, and we refer to that as the hydronium ion. So in this simple reaction between HCl and H2O, the HCl here is acting as the acid as it loses H plus. Which means that water has no choice but to act as the base. That's the only place that H plus can go. All right, so the water here is acting as the base as it accepts H plus, right? And that's the other half of our definition of the Bronsted Lowry theory. Acids donate or lose H plus, bases accept or take in protons. All right, so our Bronsted Lowry base, just to finish that discussion, bases are going to accept protons. So we call it a proton acceptor. So if something is losing an H plus, right, something else has to gain it. The H pluses don't just disappear into the ether. That doesn't happen and has to go somewhere. And whatever thing takes it up, that's the base. So in a reaction, once you've identified something is losing the other thing next to it has to pick it up, has to be the base. All right? So we end up forming on the right side two things that are related to the two things on the left. So the HCl, what is it most related to on the right side? what does it look like the most? The H3O plus or the Cl? The Cl, right? And the Cl forms when the HCl loses an H plus. So we call the Cl minus the conjugate base of HCl. It's related to the HCl just by the loss of a single proton. That's the only difference between the acid and its conjugate base. Right? You can probably identify the other pair in this. And the other two things that are related is the H2O and the H3O plus, right? These, the H3O plus forms as the H2O accepts a proton. So what do you think we will call the H3O plus? So let's backtrack. HCl is the acid. Whatever it became, we call a conjugate base. So if H2O is a base, whatever it becomes, we should call the conjugate acid of H2O. So in every single acid-base reaction, you're going to have two of these pairs, two of these conjugate acid-base pairs. And they are related to each other. The only difference between them, between these two, is just the H plus. And the only difference between these two is just that H plus that we've added. Right? That's how you can identify these conjugate acid-base pairs. And it all starts from, first of all, deciding, well, what is your acid? Whatever your acid is, the other thing right next to it has to be the base. And then from there, all the dominoes kind of fall. Right? The terms can be a little confusing at the beginning, but you have to go through it a little slowly.